Hi guys, this is Mr. Chan again, and we're going to be talking today about base e, the natural number e, and natural logarithms. And then we're going to talk about exponential growth and decay. If you need to skip parts of this video, feel free because we've already covered this in class. Okay, so what is the number e? We talked about this in class. It is basically this expression where n becomes really, really big. As it gets bigger, we end up with this special number called e. It's the natural number. It's a number used in math that occurs quite a lot. And we use it a lot in science to model quantities that grow and decay continuously. So it's usually used to model continuous growth or continuous decay. And this is the form that a natural base exponential function takes. Okay, we have y equals e to the x. That's just an exponential function where the base is the natural number e. The natural logarithm then is just a logarithm with base e. So it's exactly the same as what we've been doing, just the base now is, instead of another number like 10 or a or b or whatever, it's now the letter e, which is actually a value, 2.718 approximately. Okay, and then the natural logarithmic function, once we take this and make it into a function, it becomes y equals the natural log of x. Okay, we call this ln or ln of x, or the natural log of x. They all mean the same thing. Okay, inverse properties, again, this is exactly the same as what we've talked about before, these two properties. If we take e to the power of the natural log of x, that becomes x. Okay, that looks just like a times log base a of x, where instead of a we have e, right? That is the same as the log base e of x. Okay, so it's nothing new. That becomes x, and likewise this expression is just the same form of this, just with a being the letter e. Same thing here. This is another inverse property. We said that the log base a of a to the power of x is x, and so instead of a, if we replace a with e, we end up with the natural log of e to the power of x is just x. Okay, and this is a picture that shows you the inverse properties of these two functions, so that y equals e to the x is the inverse of the natural log of x. You can see here, this is the graph of y equals e to the x, and it's reflected across the line y equals x. So special values, these are actually the same as what we talked about before. It's just with the letter e this time, with the natural logarithms. So here we have log base a of anything, anytime the argument is 1, we'll end up, anytime the argument of a log is 1, we end up with that being equal to 0. And this is again just log base e of e, and we know that that's going to be 1. Okay? So natural logs are just like regular logs. If we were to take this expression, 5 natural log of 2 minus the natural log of 4, we could simplify this by using the power property. We could put this 5 up here, so we end up with 2 to the 5. And then with this minus, we can say that's 2 to the 5 over 4, and that's what we end up here. That's the quotient property of logs. And then that simplifies to natural log of 8. Okay, and this is just another example. You can try that one out. And again, this is just calculator practice. If you were to do this on your calculator, you would press, this is on the TI Inspire, you would press that button, and then 0.5 and enter. I think you know how to do this. This, you'd have to press Control, then e to the x, then 3. Okay, so that's how you get the ln, the natural log function on your calculator. And then you press enter, and you should get that number. Okay, and you can try these on your own as well. Okay, writing equivalent expressions. Remember that exponential expressions can be rewritten as logarithmic expressions. So if I were to rewrite example 5 in log form, I could take the natural log of both sides, because I want to isolate x, so I'm going to take the natural log of both sides. And why do I do that? Because if I do this, then I know that this part will cancel out. Okay, this is the same, because we know that the natural log of e to the x is equal to x. We talked about that in the previous slide. This whole expression here can be replaced with x, and so we end up with the natural log of 23. Okay, so this would be just the same as if I were to move this little 2 over here and bring that x down. Okay, it would be the same as that shortcut, but this is showing you the math. Same thing here, we would end up with x equal to the natural log of 6. And this, because this is really just log base e of x, right? Well, then we can, because that's the same thing as the natural log of base e of x, we can raise this to the e. Okay, if we raise both sides to the e, or to the power of e, well then that becomes, because we know that the e to the natural log of x is equal to x, this side becomes x, and this side becomes e to the 1.2528. Okay, and if you did that on your calculator, you'd get your answer. Same thing here, x is equal to e to the 2.25 approximately. Okay, so this is kind of a, yeah, this is the same thing. Okay, so let's take a look at this equation. Now we're actually solving an equation. We have an equal sign here. We want to solve for x. Okay, so how would we solve this? We want to isolate x, so we're going to bring this guy over to this side. So let's do that. So if we subtract 2.5 from both sides, we would end up with 7e to the 2x is equal to 17.5. Then we want to isolate, because this looks a little bit complicated. Okay, we want to try and get this to be by itself, because then we can probably use the natural log the inverse property of logs, right? So we're going to try and get this by itself, so we're going to divide both sides of the equation by 7, and so if we do that, we get e to the 2x equal to 22.5. And then what we're going to do is we now can take the natural log of both sides, because then we can cancel out that natural log and the e. We're going to undo that. Okay, so if we take the natural log of both sides, then we end up with 2x. Okay, this side, that expression just becomes that. Okay, and now we can solve this. Oops, sorry. Now we can solve this. And we end up with x equal to the natural log of 2.5 divided by 2, and there you go. Okay? And then you would do this on your calculator and get that expression. Alright, so that would be how you'd solve this equation. Make sure you do check your answer, because sometimes you might get an extraneous solution or an answer that does not work. So just check your answer. Okay, let's try another one. I think you can do this. This one's a little bit easier than the previous one, actually. What you're going to do is now you're going to take the natural log of both sides, right? Because we want to get rid of this e, and we want to bring that x down. So if we take the natural log of both sides, what happens? Well, the natural log of e, this right here, cancels out, and that comes down. Or you can just simply replace this whole thing with that exponent. Okay? And so what you end up with is x plus 1 equal to the natural log of 30. And then take 1 away from both sides to get x by itself, and that is your answer. Of course, you'd have to put this on your calculator, and you would get x equal to 2.401. Okay, so this is how you solve logarithmic or exponential equations that have a natural base in e. Okay, again, this is going to be the exact same thing. We've seen this before. Natural logs are no different from common logs or logs of different bases. We just want to get x by itself, so we're going to raise both sides to the power of e. And when we do that, we end up with 3x, okay, because if we raise both sides to the power of e, all right, that expression becomes that. And then we can divide both sides by 3, and we end up with x equal to 1/3, or, which is the same as dividing by 3, 1/3 e to the 0.5, and on your calculator that comes out to that number. Okay? Alright, so we talked about this in class. What were some types of items that increase in value over time, exhibiting exponential growth? We talked about things like bacterial growth, okay? Bacterial growth, or population growth. You can also have like bank investments. Hopefully they're growing. Bank investments. You can have appreciation of houses. Okay, the value of your house can appreciate, which means it can increase. Okay. Or what are some things that decrease in value? Basically anything that will, like a certain percentage of the price gets deducted every year or every time period. So things like cars. Okay, once you buy a car, the value starts to depreciate. That's called depreciation. Okay, so the value of it is falling at a certain rate, not a linear rate, but a exponential decay, exponential rate. Okay, so we talked about cars. We talked about some things like half-life. These are all examples, real-world examples of exponential growth and decay. Okay, so these are the two formulas that I want you to know when we're talking about rates that are applied every cycle. Okay, so every time period, that passes, if a certain rate is applied to a value, then we use these two formulas. The first one, this formula, is used for growth, and the inside of my parentheses, that is kind of that's like my growth factor. That must always be bigger than 1. So if you end up with that being bigger than 1, then it's a growth situation, and you should be able to compare that with what's in the problem. Just make sure that it makes sense before using this. Okay, this is the decay formula. Notice that it's pretty much the same thing except it's minus. This is now a minus sign, and this factor here, this is called the decay factor, and it is less than 1. Okay, so if it's less than 1, then it's going to be decaying. If it's greater than 1, it'll be growing. Usually this r is given to you, this r value. That should always be a decimal. Should always be a decimal. A is always the initial amount. These two are always the initial amount, and this t is always going to be the number of time periods that have passed since in the problem. Okay, so here's an example. You want to buy a 10-speed bike for $150. It loses value at a rate of 15% per year. What is its worth in 3 years? Okay, well, as you can see here, it's going to be a decay. It's going to be decaying because we're losing value, and the rate is 15% per year. So actually, let's write down what we know. We know that r is going to be 0.15, and it's a decay situation. The bike, the initial amount was $150. Okay, and the time is actually going to be in years in this case, and it's going to be 3 years. So that's the information that I know. I know that my formula is going to be probably This is a decay situation, so we're going to use this. And so that's what we have here. They use W instead of Y, but that's okay. And so once you plug this in, notice that now my decay factor, the part that's being exponentially, that's being raised to a power, that is now a value that is less than 1. Okay, so we have 0.85 here. Once you put that in your calculator, you should get 92.12, and that is the value of the bike after 3 years, assuming that it's, in good condition. Which of these are growth or decay situations? Like I said, if we have 1 plus r, if that part inside the parentheses is greater than 1, then it's growing. If it's less than 1, it's going to be decaying. So this is growing, and that one's growing. These two are decaying, okay? So these are the answers. Okay, let's write an equation. Let's practicing writing the equations for word problems. Let's look at the first situation. It says you purchased a car for $35,000. Okay, so if you were in the U.S., some of you would be able to buy a car or drive a car because you're 16. So let's say you purchased a car for $35,000. The minute you drove it off the lot, it started going down in value by 1.3%. Write an equation for its value in the future. You can see, is this a growth or a decay problem? Because the value is going down, it's going to be a decay problem, so we're going to use the decay formula, 1 minus r to the power of t. What is my a? My a is going to be this. Okay, that's my a. What's my rate? That's my rate, but remember my rate has to be in decimal form, so this, if I were to rewrite it in decimal form, I would go 0.013. Okay, so that would be the value that I'd put into my formula. Now what is my t? Well, t will just remain t, okay? But make sure that you understand that the units of t here, in this case, will be in minutes, okay? Because it says every minute the value of it is decreasing by 1.3%, which is actually pretty fast. So your answer should be, if you use this information, you should just substitute that into the formula, and you would get 35,000 times 0.987 to the power of t. Okay, and this is the same as 1 minus 0.013. Okay. The second example, you just purchased a painting as an investment, and it is supposed to appreciate its value at a rate of 3.65% each year. Write an equation for its value in the future. So what it's saying is you bought a painting, you know that it's going to appreciate in value, which means grow in value. It's going to become worth more every year, and the rate is it's going to increase at a rate of 3.65% per year. That means it's going to every year it's going to be worth 3.685% more of its previous amount. Okay, so what would be its equation? Well, this is now going to be a growth, so it's going to be a 1 plus r to the t. So that's my equation. That's my formula. What's my r? That's my r right there. It's going to be 0.0365, and I'm going to have to add that to 1. Okay, my t will be in years. My t will be in years. Now, do I know my a? I don't know my a, so let's just leave that blank, or leave that just in the form of a, and so I'm probably going to have two variables here. So yes, instead of a, they said p, but that's okay. Okay, so the value will be p times 1.0365 to the power of t. Alright, now, so we've talked about those two models, but there are actually two more models that I want you to know, and these two models will be used when we have continuous growth, continuous decay. So now instead of every time period, Okay, instead of a rate being applied every period, every time a cycle goes through, instead of that happening, now it's continually, the rate is continually being applied. So let me just write on here, anytime this is continuous, oops, continuous, okay, application of rate, application of the rate. Okay, so anytime you see the word continuous or continuously, usually that means we're going to be using these two formulas. Okay. Now what's different about these two? We see that there's an E and a K. Remember that E is just a number. E is approximately going to be 2.718. Okay. So that's going to be my base. E is going to be my base right here. A is still the initial amount. K is now just a constant. K, what is the meaning of K? It's just a constant that changes depending on the circumstances. Okay, so you'll either have to find K or use K, and K will be given to you. All right, and T is the number of years, or this could be just any unit. It could be years, months, it could be weeks. Okay, etc. It could be minutes, hours. Okay. And so this is the formula we use when we're talking about exponential growth, where the rate is continuously being applied. Or we can use this formula where we're seeing decay. Okay, and normally we'll use this with radioactive decay, but you might come across some different applications where we use the letter E to model exponential decay. All right. Okay, so let's take a look here. Here's an example, a real-world example of how we can use the exponential growth or exponential decay formulas. Okay, it says the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. All life on Earth contains carbon-14, which decays continuously at a fixed rate. The half-life of carbon-14 is 5,760 years. That is, every 5,760 years, half of a mass of carbon-14 decays away. What is the value of K and the equation of decay for carbon-14? Okay, now what is the value of K and what's the equation of decay? All right, so let's make sense of this problem first. So what is half-life? Half-life is the time that it takes for a substance to disintegrate. Okay, this is actually a chemistry type problem, but you'll see that all life on Earth has carbon-14. It's a special, it's a substance, and it decays continuously at a fixed rate. Okay, so the half-life of carbon is 5,760 years. That means if I have a chunk like this, half of it will disappear, half of it will change. It'll decay it'll decay and it'll change into something else chemically. All right, and so the time it takes from my 1 kilogram to get to half will be 5,760 years. Okay, another way of thinking about this is if I have 1 kilogram at time 0, after 0 years have passed, it'll be just 1 kilogram, right? Well, after 5,760 years have passed, it'll now be 0.5 kilograms. Okay, so the weight of the actual chunk might change, it might not, but the substance will change. So there will only be half of the original amount left. Okay, so what's the value of K and the equation of decay for carbon-14? Now, let's think about this. Okay, so at time 5,760, I'm going to have half of my original. So I don't know what a is, I don't know what my original amount is, but if we leave it as a variable, we know that half of it will be left over, so we can use this formula that talks about radioactive decay. All right. So here's the formula. If we put t, if we put 5,760 in place of t, then we can say that the final amount, because this is our final amount, right? Right here, that's our final amount. This will become half of my original. So at time t, at time 5,760 years, my y value, or the amount that I have left over, will be 0.5a. And then we can solve from here. The a's will cancel. A's will, we can divide these, take these out. These a's will cancel. And then we can solve from here. Now how do we solve this? This is just a problem like we did in the previous slides. Okay, we can take the natural log of both sides. And once we take the natural log of both sides, then we end up with the exponent dropping down, and using the inverse property of exponents and logarithms, we get this. And we can solve for k by dividing both sides by negative 5,760. Okay, and if you do this on your calculator, you'll get approximately 0.00012. So that's my value of k. And so over here, this is now my equation, because all I do now is I don't know my initial amount, I don't know my time, but I can create a general formula for carbon-14. This is the equation of decay for carbon-14. Okay, so if I just know my initial amount and I know the amount of time, I can calculate how much carbon-14 I'll have left over. Okay, last example. Let's apply exponential growth to population. As of 2005, China was the world's most populous country with an estimated population of 1.31 billion people. The second most populous country was India. So these are statistics from 2005. They could have changed now. But let's keep reading. The population of India and China can be modeled by I of t equal to 1.08 e to the 0.0103 t. And the population of China is c of t equal to 1.31 e to the power of 0.0038 t. Okay. According to these models, when will India's population be equal to China's? Okay, so when will their populations be equal? So let's first look back to these functions. What is this? This is the population of India, where I is the population, and it's a function of time. Okay, it's dependent on time, and c of t is the population of China, where t is the c is a function of time. Okay, so how can we set this up? We want to find the time, so we want to find t. What is t when c of t and I of t are the same, right? So that's what we're really looking for. When are those two populations going to be equal to each other? All right. So let's see. How would we set this up? Well, we're going to set it up by setting I of t equal to c of t. Right? And that makes sense. And then all we have to do is solve for t. So if we set it up like this, now we just need to isolate t and solve. But we have a problem here. Okay, normally we would, if this was a nice easy problem, you know, if these values weren't here, we could just take the natural log of both sides. But those are there, and so those e's won't cancel quite as nicely. But what can we do? Okay, well, we can still take the natural log of both sides, and if we do, we end up with this, okay? Now, this is still pretty messy in here. Okay, this whole thing is inside the natural log, and that's kind of messy, isn't it? So let's break it into a simpler problem. And what we're going to do is we're going to split up this into two. These are actually factors. Okay, These are actually two numbers being multiplied together, and so we can actually use our product property and split them up into separate logs. Okay, so now I know that this is going to be a nice number. Well, at least I can get rid of my natural log, okay, and my e, and same with this number over here. Okay, these two numbers will simplify, and so we end up with the natural log of 1.08 plus the exponent, or the original exponent, and over here we have the natural log of 1.31 plus that exponent. Okay, and now we're going to isolate our terms with t in them, and we isolate our t, and this is what we get. Okay, so then we put this all in our calculator, and we should get t equals 29.70. So that's the number of years that it's going to take for India to catch up to China. Okay, according to these models, if these models really were true. All right. So that's an application problem of exponential growth. Population growth often problems will use the letter E. Okay, when we're talking about models for population growth. Okay, this is your assignment. Please try these problems out and let me know if you have questions. Remember that the test will be in 2 blocks. Next block will be our review session, and then we'll have the test. So, all right, thank you guys.